Okay, now you know what a capacitor is and what the capacitance of that capacitor is defined, and we have done 3 examples on how to calculate the capacitance of the given system. And you have seen that the capacitance is the quantity which only depends on the geometry of the capacitors. So, you've known that we've got to do some work in order to bring the electron from one conductor across the electric field and put it on the other conductors. And this process requires work, so we have to put our work in order to remove all of these charges. So the next concept we are going to learn about the energy stored in the capacitor. We are going to learn the concept of the energy stored in the capacitors. So what we have the following. So we know that we could have any metallic object, and then what we do, we remove the electron from this conductor and put it on this conductor. So this got a positive charge and this got a negative charge, and then we create an electric field between these two. We create an electric field between these two, and we say that we store the energy inside this capacitor. So what we know, if we try to plot the charge stored on the capacitor against the potential difference V12, let's call it just V. So V12 is the potential difference between these two conductors. From the definition of the capacitance C equal to Q divided by V, and this C, as you have just seen, it is independent of Q and V. This one only depends on the geometry of the capacitor, so it is a constant. So this C here, is a constant. So this one is a constant value for given capacitor. So C, the capacitance, is a constant value for a given capacitor. So if you plot a graph of Q against V, you will have a straight line, and this straight line passes through this zero. And no wonder the slope of this graph is actually the capacitance C. If we think about the energy stored in this capacitor, we have to talk about the work done in order to bring the charge Q across these two conductors. So let's say that I'm going to remove actually a minus sign. So it is minus dq from this conductor number 1 to conductor number 2. So I'm going to do the work. I'm going to do the work. And this work done, dw is given by minus dq times the potential difference. So I'm going to go across V from 1 to 2. So I've got to multiply this V2 minus V1. And we know that this V2 minus V1 is negative. So this quantity here is simply minus V. So then my work is dq times V. dq times V. So if we want to get the total work, I've got to integrate this from 0 to W, and here I've got to integrate it from, so I start from 0 charges from no charge up to Q. So I've got to do here integration from 0 to Q, and you see that V is Q over C. So I have these equations, and C is a constant. So I bring 1 over C outside, and you get 1 over 2 Q squared from 0 to Q. And this is given by a half Q squared over C. So you see that this work is the thing that turns into the energy stored in the capacitor U. So I've got U equal to a half Q squared over C. And you see that Q over C, so here I've got Q, here I've got V, so Q over C is V. So I'm using this relationship to change this into a half QV, or I could even write Q equal to C times V and plug this in. So I've got a half CV squared, a half CV squared. So basically, you can write U, the energy stored in a capacitor, equal to a half QV equal to a half Q squared over C equal to a half CV squared. And this is the energy stored in the capacitor, and this is the energy stored in the capacitor. My questions, and maybe your questions as well. Where does the system store these energy? Where does the system store this energy? Think about it while I am rubbing the board. Think about what happened when you increasing the energy. Think about the way what happened when you increase the energy stored in the capacitor. What changes in the system? So what we know that when we increase the energy, and the way we increase the energy is we store more charges, and when we store more charges, we get more electric fields. So you see that when we store more energy, we get more electric fields. So it means that the energy stored in the capacitor is stored in the electric fields. So the answer to this question is energy is stored in the form of electric fields. The energy is stored in the form of electric fields. How do we understand this? The way to understand this, we look at this example, parallel plate capacitor. We look at a parallel plate capacitor. So we've got a uniform electric field between these two parallel plates. We know that U is a half CV squared. We know that C is a constant, and in this case it is given by epsilon naught A over D. V is the potential difference, and in this case is E times D, where D is the gap between these two plates. E, if you know how much charge you can store in this capacitor. So we know the surface charge density sigma. So we know that E is sigma over epsilon naught times D. But just leave it the way it is like this. So U over the volume. So the energy per volume of this capacitor, and this capacitor is got a shape of a box. So this quantity we call it energy density, and we call this quantity small u. When I write small u, you see that I have a curly head here. So u is u over the volume, and the volume is the area times D. So I've got a half C, which is epsilon naught A over D, times V squared, which is E times E squared, divided by A times D, divided by A times D. So this is the term we want to calculate. So you see that this A cancel with this A. This D make this D square and cancel with this D square. So we've got a half epsilon naught half D square. So you see that the energy density has this form, the energy per unit volume. A half is a constant, epsilon naught is a constant, but E, it is the electric field. So you see that the energy stored in this capacitor, it is stored in the form of electric field, and the energy is proportional to the electric field square. Even though we derive this equation for this parallel plate capacitor, but this equation is true for every capacitors. It's true for every capacitors. It's true for every capacitor, and it's true in general. When you see electric field, you can calculate its energy using this expression of energy density. Let's wait for the ball to run. The next concept we have to discuss is connecting capacitors. Connecting capacitor. So first, let's consider when we connect it in series. What does this mean by connecting capacitor in series? So this is a simple form of capacitors. So we use two parallel lines, and these two lines they've got the same length. So you see that when we connect these capacitor in series, what I really mean, I mean that I join one hand with another hand of the next capacitor. So let's say that this has the capacitance C1 and this has the capacitance C2. What we want to know that, so this is point A, point B, and here is point C. What we want to know that if we are going to replace these two capacitors by just one between point A and point C, what capacitor shall we use? And we call that the equivalent capacitor, because this capacitor act as if it gives the same result as these two capacitors connected in series. To understand this, we know that if we put a charge plus Q here on this plate, when we charge up the capacitor, you see that for a parallel plate capacitor, there is no electric field outside. So when we enclose this Gaussian surface, it means there is no electric flux. So I know that if I put a charge plus Q here, it means that on this side, I must have a charge minus Q. And on this plate, I must have a charge of minus Q here. So this is small q, and here I must have the charge of plus small q. How do I know this? Well, I know that altogether when I enclose this with the Gaussian surface, there is no electric flux. That means the total charge inside must be zero. So if this is plus Q, this must be minus Q. And you see that on this plate and on this plate, we connect these two plates together. So the total charge on these two plates must add up to zero due to the conservation of charge, because before we connect these two capacitors, both of them are neutral. So if you've got a charge of minus small q here, it means that you've got a charge of plus small q there. Next, if I'm enclosing this capacitor by this box, we know that there is no electric field outside, so the net electric flux must be zero. That means the charge on these two plates must also sum to zero. So we've got plus Q minus small q equal to zero. This means that this Q equal to the big Q. So actually what I do, I can change this charge to big Q and this charge to big Q. So this is the situation we have when we connected this thing in series. And you see that in equivalent capacitor, when we join up these two hands, minus Q and plus Q cancel. So what we only have plus Q here and minus Q here. What we could write down, we can show that VAC, which is VA minus VC, equal to VAB plus VBC. And if you expand this, you will understand why. So you get VA plus VB plus VB minus VC. And you cancel these two, so you get VA minus VC, and on the left you get VA minus VC as well. So that's why this equation here is correct. So give it a tick, a tick. What is VAC? VAC, if you look at this, for the definition of capacitance, C equal to Q over V. So V is Q over C. So I've got Q over C equivalent here, and this equal to VAB, which is Q over C1, plus Q over C2, and this is VBC here. And finally, you see that these Q are equal. So we cancel this Q, Q, and Q. So we've got 1 over C equivalent equal to 1 over C1 plus 1 over C2. And this is the way we calculate the equivalent capacitance when we connect these two capacitors in series. Next, we connect these two capacitors in parallel. So when we connect these two capacitors in parallel, we have A, C1, and B here. And then we connect C2 with this B. So you see that the equivalent capacitor will be like this, A and B, and this is the equivalent capacitance. So what we know here, we know that V across C1 and V across C2 are the same, and this equal to VAB because their hands joining the point A and point B. If C1 is got the charge plus Q1 minus Q1 and then plus Q2 minus Q2, so that means the equivalent capacitor must give the same result, so it's hold the total charge Q and minus Q, where this Q equal to Q1 plus Q2. And you see that from the definition of the capacitor, C equal to Q over V, so Q is C times V. We've got the equivalent capacitor times VAB equal to C1 times VAB plus C2 times VAB. And as you see, VAB cancel. So we've got C equivalent equal to C1 plus C2, and this is the result when we connect the two capacitors in parallel. When we connect the two capacitors in parallel. Okay, now we've got the last topic left, and that topic is the topic of dielectric. But before we move on to that, let's look at two examples. This example is the first example. So in this example, we've got C1, the first capacitor, the second capacitor, and the third capacitor. And from this diagram, you see that C2 is connected in parallel with C3. And then we connect this system by C1 and we connect them in series. Finally, we charge the whole capacitors by this battery which has the electromotive of 5 volts. We are going to learn the concept of electromotive in the next lecture. For now, you think that this battery just give the potential difference of 5 volts to this whole lot of capacitors. What the question say, the total charge stored in this system in C1, C2 and C3 is 40 microcoulombs, and this is Q1 plus Q2 plus Q3. And the question asks you to calculate C1. And the question asks you to calculate C1. So how do we do this problem? So you see that we can view these three capacitors as one equivalent capacitor. So here I've got C equivalent and it's connected to a battery. So you see that the symbol for battery, we've got two lines as well, but we've got one is smaller or shorter than the other one. Unlike the capacitors, we've got two parallel lines of the same length. So in this case, we know that the total system can hold up the charge of 40 microcoulomb. So the equivalent capacitor will be Q, which is 40 microcoulomb divided by 5 volts, and this gives you 8 microfarad. So what we want to calculate the total capacitance here to get the equivalent capacitance of 8 microfarad. So let's start with these two here. These two, they are connected in parallel. So we get 1 over C equivalent here equal to 1 over C1, or actually 1 over C2. Oh, they are connected in parallel. I'm very confused. This with the formula for the resistors. So when they are connected in parallel, the equivalent capacitance will be C2 plus C3, and this gives you 8 plus 8. So you get 16 microfarad. So now the system here becomes C1 connected in series with this 16 microfarad. And this system will turn into the equivalent capacitance of 8 microfarad. So when they are connected in series, you get 1 over C equivalent equal to 1 over C1 plus 1 over C, let's call this C4. So you get 1 over 8 here. The equivalent capacitance is 8 equal to 1 over C1 plus 1 over 16. So you get 1 over C1 equal to 1 over 8 minus 1 over 16. And then you've got 2 over 16, 1 over 16. So C1 equal to 16 microfarad. And this is the answer. And this is the answer. C1 is 16 microfarad. C1 is 16 microfarad. If you want to calculate the energy stored in the total system, you can use U equal to a half Q times V. So I've got a half 40 microcoulombs times 5 volts, and this gives you 100 microjoules. So you can store the energy, the total energy of 100 microjoules. And as you see here, C1 is also 16 microfarad, and we connect these to a battery of 5 volts. That means the voltage is changed between these two capacitors by 2.5 volts and 2.5 volts. So this C1 will store the energy U1 equal to a half C, which is 16 times V squared in 2.5 squared. So you get the total, the energy for U1. Let's say this is 8, 6.25 times 8. 50 microjoule. So that means these two capacitors has the energy of 60 microjoules as well. So each will store the energy of 25 microjoules and 25 microjoules. So you say 50 at 25 and up to 25 you get 100. So the total energy must be the same when you do these calculations. So it is a good check whether you've got the correct answer or not. example number 2. We know that the capacitance depends on the radius. So I've got this big ball with the radius big R and this small ball with the radius R. And what we do first, we put up a total charge Q on the surface of this ball of these conductors. Then we connect these two metal balls by a wire. So the charge from the big sphere will transfer to the small sphere, part of it, not all. If you ask when will it stop, the answer is so easy. It will stop when the electric potential between these two balls are the same. So V big equal to V small, this is when it will stop. In this system, what we know that if you turn to the final state where it has charge Q1 and on the V box it has charge Q2, so we know that Q must be equal to Q1 plus Q2, and this is the first equation, and this is the first equation. What else do we know? We know that the potential on the surface of these two spheres must be the same, so Vs equal to Vb, and the definition of for the capacitance C is Q over V, so we know that V is Q over C. So I've got Q1 over C1, and C1 here is small r over K, so I've got R times K equal to K Q2 divided by VR. And you see that this K cancel, this K cancel. So I've got Q1 over small r equal to Q2 over VR, and this is 2. So what we can show that you can write Q2 as Q1 equal to Q2 times R over R, and you put this in the first equation. So you get Q equals to Q2 over R times the small r over R plus 1 plus 1. So Q2 is given by this equation, and then you solve in the same way with the same technique. You get Q1 equal to R over Q divided by R plus R. So you get these two relationships. What we want to calculate, the surface charge density sigma for this small r, and this is given by Q1 divided by 4 pi r squared. And you see that Q1 is big Q over R divided by R plus R divided by 4 pi R squared. So you get this R cancel this 1 R here. So you get Q over 4 pi 1 over R plus R. Then we look the same. We do the same for this big sphere. So we get the charge density sigma R equal to Q QR R plus R divided by 4 pi with R squared. So you get Q over 4 pi 1 over R times R plus R. So you summarize this as a result here. So you touch these two spheres, you get Q1 equals to R over R plus R times Q, and Q2 equal to VR times Q, but the surface charge density sigma 1 is given by Q over 4 pi R plus R 1 over R, and sigma 2, sigma Q1, let's take sigma small and sigma R, we get Q over 4 pi R plus R 1 over R. So what you should consider here is the surface charge density. So this term in the bracket are the same. So you see that this sigma is actually inversely proportional to the radius. What does this mean? It means that for this small sphere, the radius is small, the surface charge density sigma R is greater than the surface charge density of this sigma big R. So on the large sphere, it's got less surface charge density. So this example tells you that if you've got metal and you've got a pointed part like this, most of the charge will concentrate on this part rather than this part. Where you see a pointed area here, most of the charge will concentrate on those parts. And this, we use this concept to build up what we call the lightning rod. So you see that if you've got a tall building, so this is a building, so it's got a window, so this is a building. On top of this building, you will get what we call a lightning rod. The lightning rod, สายล่อฟ้า and at the pointed at the tip of this lightning rod, they will build it to be very sharp, such that it's got most of the charge onto this part here. So you see that the lightning rod will be up, and their tips will be pointed and very sharp, such that most of the charge will concentrate on this part here. And because most of the charge concentrated on this part, when the lightning strike, it will strike at this part, at this pointed at this sharp pointed area here. So this is the application of this exercise. Okay, now we come to the last topic, and the topic of dielectric. So dielectric is simply the synonym of insulator. It's not quite. So let's see what the dielectric is. So the question here is, how do we increase the capacitance of capacitor? How do we increase the capacitance of a capacitor? Suppose that we've got two parallel plates. The capacitance is epsilon naught A over D. You might say that, okay, why don't we increase the area A and then C will increase? This is perfectly fine. But think about it. How large can we increase the area? If you've got a capacitor of this big, will you carry it around, or could you fit these big capacitors into the electronic device? And the answer is no. So it means that doing this, you can increase it to some extent, but it's not a good way to do that. You might say, why don't we decrease the separation gap here? Then C will increase. This is also true, but think about it. E equal to V over D. So what happens when you decrease D? The electric field increase. And when the electric field increase, so between this capacitor is air, we know that for air, if the electric field is larger than about 3 million volts per meter, you get a spark. What does it mean by spark? It means that the charges transfer from one plate to the others. And this is no good for the capacitors. It is no good because it means that you loses the charges you stored on the plate. So increasing A and increasing B, you can do it, but you can do that to some extent. You cannot continue doing this. You cannot continue increasing A and increasing B to get high capacitance. That actually is a good way to do this. So you see that we get a spark, and spark is no good. So people think that, so suppose this, we've got a positive plate capacitor. So we get positive charges on this plate, and here is the negative plate. To prevent the spark, we say that, why don't we insert an insulator between these two plates? So we insert this insulator, and this insulator we call it dielectric. So what happens after you inserting this dielectric between this capacitor? What we have, these negative charges will induce charges in this insulator and positive charges in these insulators. Actually, let's do white draw with a red color. It's better. So we find a red chalk. So this positive, positive, and positive, negative, negative, and negative. And this process we learned already is called polarization. And the charges induced in this insulating material, we are going to call it induced charge, or sometimes they call it bound charge. So I might use sigma bound or sigma induced. They are the same things here. They are the same things here. Apart from this, I have a charge I store on the capacitor, and let's call this Q-free or free charge. And free charge is the useful one. Induced charge is the useless one, because these charges are fixed in the insulator. You can't use them. But this free charge will move around. It's not around. It could move around, and then we can bring this free charge out and turn it into electric current, and hence the energy. What we know that there must be the polarization effect happens here. This free charge will create the electric field E0, and this E0 is the electric field before we insert in the insulator. However, the induced charge will also create the electric field E induced, and as you see here, the induced electric field always point in the opposite direction to the electric field produced by the free charge. So, the net field equals to the electric field before we inserting the dielectrics. Minus the induced electric field. And actually, we don't know how to calculate this induced electric field. So what we do, you use a probe to probe the electric field inside this material, this dielectric constant. So what we do, we use the new constant kappa, and this kappa is what we call dielectric constant. So we rescale the old field by this constant kappa to get the net field here. Actually, I should draw this with the yellow, with the orange chalk. So you use the previous field, the old field, divided by kappa, then you get the net field. And you see that solving these equations, the induced field will equals to E0 1 minus 1 over kappa. So you can get the induced electric field from this equation as well. And as you see now, the charge stored on the capacitor is still free charge. So it is sigma F times the area A. The voltage now is E times D, and this E is the net field. So it is E net become the separation D, and you see that the net field equal to the old field E naught divided by kappa times D, and the old field is related to sigma free divided by epsilon naught times D over kappa. Using these two, the capacitance C, the new capacitance equal to Q over V. So you get sigma FA divided by sigma FD over epsilon naught K, and this sigma F cancel. So you get K epsilon naught A over D, or this equal to kappa times the whole capacitance. So you see that by inserting the dielectrics, we have this relationship. E net equal to the previous field divided by kappa. C mu, the new capacitance, equal to kappa times the old capacitance C naught. So you see that the capacitance increases in this way when we inserting the dielectrics in between. Yes. Good. Okay. From these equations, you can calculate about, well, the induced charge in the insulator using the induced field, which is sigma induced divided by epsilon naught equal to the old field, which is sigma phi divided by epsilon naught. You've got the surface charge density of the induced field equal to the surface charge density of the free charge 1 minus 1 over k. This is the induced surface charge density equal to the free surface charge density times 1 minus 1 over k. One can write the induced charge equal to the free charge times 1 minus 1 over k. So we've got those relationships as well. Finally, we are going to derive Gauss' law in dielectric. Gauss' law in dielectric. So if we consider Gauss' law, E dot N dA, this is the electric flux, equal to the total charge inside divided by epsilon naught. So this E dot M here is the perpendicular electric field to the surface dA. On the right hand side, if you get Q free minus Q bound divided by epsilon naught, so you see that if I've got a parallel plate capacitor of positive Q free, and if you've got an insulator, you have a negative induced charge. So when you close it with a Gaussian surface, it's Q free minus Q bound or Q induced. Let's change Q induced. And you see from this equation, Q free minus Q induced equal to Q free divided by kappa. So I can change this to Q free divided by kappa epsilon naught, and then I bring kappa to the other side. So my Gauss law becomes kappa E dot N dA equal to the total free charge. So you see that if you use E, we have to use the total charge. But here, we are going to compensate the effect of the induced charge by this factor kappa. So now on the right hand side, we don't need the induced charge anymore. What we only want, we want the free charge divided by epsilon naught. And this is Gauss law in dielectric materials, where we use the dielectric constant kappa to compensate the effect of induced charge. So, hope you get all the idea of these lectures. And that's the end of this lecture.